Hi there, folks. Today we're going to be doing the entirety of Chapter 6. Chapter 6, it's a quick one. Chapter 6 is really applications of integration. And there are a ton of applications to integration, or applications for integration. But when it comes to medicine and biology, the main application is going to be related to differential equations. And differential equations is a Chapter 7 topic. And so the applications which are introduced in Chapter 6, they do have value. You can use them, but they're not nearly as important as the Chapter 7 applications. That said, there are 4 main applications that we're going to be going through. And each one is very, very quick and not too difficult to use, except for possibly 6.3. 6.3 has a couple of mean ones, but the rest, they're very, very intuitive. And so the first is, how do we find the area between two curves? Well, you just subtract. It's kind of like if you have one shape and you want to remove part of the area, you would just subtract. How do you find the average value of functions? And the average value, it's an average. And so you just find the total area and you divide by the length. And then how do we find the volume of a rotated object? And as a hint, we know how to find the volume of something which is rotated. It's pi r squared times the height. That's the formula for the volume of a cylinder. And so instead of breaking things into rectangles, we'll be breaking things into cylinders. These are some of the easier ones where really all you have to do is just use a formula. As long as you have the formula, you can do all 3 of these types of applications with no issue. The other one is this further applications to biology. And those are some more advanced models. Basically, when you are thinking about what the definite integral represents, the definite integral can represent the area under a curve, but what types of things can be modeled by the area under a curve? And it turns out you could basically model anything using that. And once you have that, well, the integral is a tool for finding that area. And so if you know the growth rate of a population, the area under that curve is going to be the entire population. And it doesn't matter if we're talking about population of fish or population of bacteria or population of bunny rabbits. It does not matter. We can use the definite integral to figure it out. As it says here, this is really just kind of getting us ready for the Chapter 7, where you're going to see the main applications, which is differential equations. As we've mentioned in the course, differential equations are used to model everything. And in order to solve differential equations, you need to use the antiderivative. That said, it's only 6 pages. Let's see if we can get through this. And so the first application is the area between 2 curves. And in this case, I have it broken up so that we have 2 different approaches. One is the area between 2 curves which do not cross, and the other is the area between 2 curves which do cross. And so to find the area between 2 curves which do not cross, really you just have to find the area of the top and subtract the area of the bottom. Or we can actually just subtract the 2 functions and find the area underneath that. Let me show you the visual for this and why this works out. And so let's suppose that we have 2 functions, and I'll just create a quick Cartesian coordinate system, and we'll call this function g of x. We'll call this function f of x. And so if we want to find the area between these 2, which would be something like this, one approach would be to find the area of f of x down to the x-axis. And so everything from here down, which would be the integral of f of x dx from a to b, if we are saying that this starting point is a and this ending point is b. And then we would need to subtract the area of just g of x. And so if we subtracted the area of just g of x, which would be this bit down here, then that would be minus the integral from a to b of g of x dx. But we know from the rules for integration that we could actually just combine this into a single thing. And so we could just rewrite this as the integral from a to b of f of x minus g of x dx. And so that's the principle behind this. And so this expression right here would find this area, the area between the two curves. There we go, do some cross hatching so that we really see it. Now, the question becomes, what if one of the functions crosses the other function? And it turns out it's almost the exact same process. And so let's do the same graph, but now we're going to have f come down like this, and we'll have g come up like this. And we'll still be going just from a to b, let's say. But then we're going to have a third position over here at c. Well, in order to figure out what the area is between these two curves, it's still going to be the exact same process. It's still going to be the top minus the bottom, because that's how you calculate area. The difference here is the function which is on top changes when you hit c. And so the formula for this would be the integral from a to c. And on the interval from a to c, we see that the function f of x is on top and g of x is on the bottom. And so this would be a to c of f of x minus g of x dx. And then we would add the integral from c to b of g minus f. And so in both cases, we're really doing the same thing. We're just taking the top function and we're subtracting the bottom function. And then we're doing our standard integral. As long as we do that, we'll find the area between those two curves. And that's kind of what's outlined here. And so the area between two curves which do not cross, it's just the top function minus the bottom function. If you have two curves which do cross, the first step is figure out where the two functions cross. And you can do that by setting the functions equal to one another or using the graph or whatever methods you're able to use. And then you just create your definite integrals so that you're integrating the top function minus the bottom function. And then after you've done that, just add up all of your integrals together. And here is an example which is already worked out for us. It doesn't actually do the integration for us, but we can see what's going on here. And so find the area of the region bounded between the functions f of x equals negative x squared plus 2 and g of x equals x on the interval 0 to 2. And so from 0 out to 2. Well, in order to do that, we notice that the two functions cross at 1. And it turns out they both go through the point 1, 1, which is kind of nice and a little confusing, but that's all right. And so we set up our first integral to go from 0 to 1. And on the interval from 0 to 1, our parabola, our f of x function, is on top. And so we would do f of x minus g of x, which is here, f of x minus g of x. For the next one, integral from 1 to 2, on 1 to 2, well, we can see that our g of x function is the one on top. And so we do g of x minus f of x. Then comes the tricky computational part of actually doing all of the integration, and I skipped all of those steps, but you should try it out. See if you can actually expand all of this and see if you get the answer of 3. Note that when you do this, you're going to get 12 terms out of it, because when you do the antiderivative for this first section, you'll have 3 terms, but then when you evaluate it, you're going to get 6 terms. And then same for this one. And so in total, you'll have 12 terms coming together to give you this answer of 3. That's why often when you have 2 curves which cross, it can take a little bit of time to do them. I have a few problems here. First one is x plus 2 and x squared. And it just says find the area of the region bounded between the two functions. And so it doesn't even say a start point or an end point. It just says find the area of the region bounded between them. The good news is that means that we're only going to have one region which we're dealing with. Bad news is we have to find both the start points and the end points. And so f of x equals x plus 2, and g of x equals x squared. Let's see if we can do this one from scratch. And so first things first, it might help if we had a graph of this. And if you want, you could go to Desmos to graph it out. But let's just graph these by hand. These are very, very nice functions. And yeah, I bet if we go from like -1 out to 4, we'll be good. And 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4. And so the first function is x plus 2. So x plus 2 is going to be a line. It starts at 2. And we can graph this thing like the back of our hands, I hope. If not, we definitely need to go back to Algebra 1 and practice. There we go. So this is f of x. The next one is g of x, which is given by x squared. Another one which we should be able to graph no problem. And there we go, and there we go. And so the area which we are looking for is this area in here, because this is the area which is bound between the two functions. It's the only one which is bound between the two functions. If we were to go outside of that, we could bound them if we had some ending point or starting point, but since we weren't given a starting or ending point, this right here is our start and our end. We can also see that one function is above the other function on the entire interval. And so this one's going to be pretty straightforward. We would say that this is going to be the integral from -1 to 2. Oh, let me put those in the right location, from -1 to 2. And then it's going to be the top function minus the bottom function. I didn't label that bottom function. Let me label that real quick. G of x. And so our function f of x is the one on top. And so we'll say it's x plus 2 minus our g of x, which is x squared. And now we just have to integrate. And so we can integrate this one. Shouldn't be too bad. Integral of x is going to go to an x squared, and we're going to need a 1/2 out in front. Plus 2 is going to go to 2x. And then the negative x cubed is going to go to a minus 1/3 x to the third. And then we're going to evaluate these at 2 and at -1. So using the fundamental theorem of calculus, we get 1/2 of 2 squared plus 2 times 2 minus 1/3 of 2 cubed. And then we're going to be subtracting all of the ones evaluated at -1. So oftentimes I'll just put this in brackets and then I'll subtract the 1/2, and then it's a -1 squared plus 2 times -1 minus 1/3 times -1 cubed. Now, there's going to be a lot of sign mistakes and things like that, so definitely be careful with this. But 2 squared is 4, 1/2 of 4 is 2, plus 4 minus 1/3 of 8 would be 8/3. And then we're going to have a negative 1/2 squared is positive 1. And so it becomes a negative 1/2. And then we're going to have a 2 times negative 1 is negative 2, which goes to positive 2. And then 1/3 of negative 1 cubed. Well, negative 1 cubed is negative 1. So this becomes a positive 1/3, which then becomes a negative 1/3. 2 plus 4 plus 2 is 8. Minus 8/3 and 1/3 is 9/3. And so that's going to be a, what is it? A minus 3. And then we have a minus 1/2. 8 minus 3 is 5. 5 minus 1/2 is 4.5. Now, I don't know that I trust all of my computations, and so I'll probably throw this into a calculator just to double check. And hopefully my calculator gives me the same answer. If not, I'm in trouble. Minus 8/3 minus negative or minus 1/2. Then it is minus 2 and a plus 1/3. And I get 4.5 on my calculator. And so this is the type of problem which you'll be dealing with. Notice most of this is really just arithmetic. The only calculus bit was this step right here, where we went from our graph to create this formula, and then we did the antiderivative. Once we did the antiderivative, everything else was just evaluating the antiderivative and simplifying, which is just a ton of arithmetic. And it's very easy to make little mistakes when you're doing that. And so be careful, just be careful. Let's do one more of these. All of these look equally bad, but number 3 looks especially fun. And so let's try number 3 real quick. Because I believe those are going to cross, and it might not be intuitive where they cross at. And that could make it very fun. And so in this case, we're going to be dealing with find the area of the region bounded between the equations x equals 0, x equals 4, y equals 1 over x plus 1, and y equals x minus 1 over 2. And so for this, I'm going to go to Desmos real quick, just to see what the graph looks like. And so here's our good friend Desmos. We have x equals 0. We have x equals 4. So those are the starting and ending bounds. And then we have y equals 1 over x plus 1, which is in green. And then we have y equals x minus 1 all over 2. And if we want, we can restrict these so that they're just going on the interval from 0 to 4. That'll make it so that it's a little bit easier to see what we're dealing with. 0 less than or equal to x less than or equal to 4. And there that is. Now with Desmos, I think we could even rename these as f of x and g of x. And we could even ask it to shade the stuff in between these. And so we could say, when is f of x less than or equal to y, which is less than or equal to g of x? And then we could say, when is g of x less than or equal to y, which is less than or equal to f of x? And so this gives us the two regions which we are trying to determine. We want to figure out the area of these two regions and then add them together. Now, the question is, where do they cross? And 1.732, my guess is most folks don't recognize what that irrational number is. And so we would need to actually calculate what this value is. The good news is, once we have that, we can figure out which one's on top and which one's on the bottom. I'll do a quick sketch on my own whiteboard so that we can at least have a visual of some form. And I'm not going to do it so that it's precise by any measure. I just want something so that I can visualize which one is on top and which one is on the bottom. And so we know we are going from 0 to 4. I will call the first function x. I will call the second one g of x. And I will even have them color coded to make it easier for me. Cool. And so what we need to do is we need to figure out where they are crossing. Because once we figure out where they are crossing, everything before that will be doing f minus g. Everything after that will be doing g minus f, because the f function's on top at first, and then the g function is on top at the end. To figure out where these two functions are crossing, we need to set them equal to one another and solve. That'll tell us the x value where these two functions are the same. And so we would say 1 over x plus 1 is to be equal to x minus 1 over 2. We can cross multiply, which gives 2 equals x squared minus 1, because it's the difference of two squares. Adding the 1 to both sides gives 3 equals x squared, which tells us that x is equal to plus or minus the square root of 3. Since we are just looking at this positive region, that tells us that this spot where they're crossing is going to be when x is equal to the square root of 3. And if you check, the square root of 3 is going to give you that 1.7 number. And so now we have our bounds. And so we're going to be doing our first integral from 0 to the square root of 3. And it's going to be f minus g. So that is 1 over x plus 1 minus, I'll distribute everything and even clean this up a little bit. So that'll be minus x over 2, and then it'll be plus 1/2. Plus the integral from square root of 3 to 4, because that's the second interval. And now it's g of x, which we could rewrite as x over 2 minus 1/2 minus our 1 over x plus 1. Parentheses and a dx. This is going to have a number of terms once we are done with it, but that's okay. And so now we actually have to integrate these. And integrating it is going to be messy. And so the first one, integral of 1 over x plus 1. Seeing if we remember our antiderivatives, that should give us a natural log, correct? Because the derivative of natural log is 1 over stuff. And that's the one that I told you you'll get confused over and over again. Minus x over 2 is going to go to x squared over 4. Plus 1/2 x. This will be evaluated from 0 to square root of 3. Plus, now we have to do the same for the second one. You'll notice the integrals are going to be the same, though. The integral of x over 2 is going to become x squared over 4 minus 1/2 x. And then it's going to be minus a natural log of absolute value of x plus 1. And this one's evaluated from square root of 3 up to 4. Now comes the fun bit. And so we have to take all of those and we have to evaluate them. And this is where we're going to get 12 terms out of this. And so this is going to give us equal the natural log absolute value of square root of 3 plus 1 minus, and then it's going to be square root of 3 squared over 4 plus 1/2 times square root of 3. And then it's going to be minus all of the things evaluated at 0. So that'll be natural log of absolute value of 0 plus 1. It'll become a plus 0 squared over 4. Then it'll be a minus 1/2 of 0. And then it's going to be plus all of these evaluated at 4. So 4 squared over 4 minus 1/2 of 4 minus natural log of 4 plus 1. And then we have to subtract all of these evaluated at the square root of 3. And so it's going to be the square root of 3 squared over 4 minus 1/2 of the square root of 3. But now it's a plus. Always be careful with those signs. Those signs throw everyone off. Plus square root of 3. And then it'll be a plus the natural log absolute value of square root of 3 plus 1. And now, if you want the exact answer, you can get the exact answer. Or if you prefer to get an approximation, you can plug it into a calculator. I might go the approximation route for this one just because, well, the exact might actually be easier, to be honest with you, because the natural log of 1 is 0. So that goes away. 0 squared over 4, that goes away. 1/2 of 0, that goes away. And so basically, this entire row is gone. Square root of 3 over 4 is 3/4. And so it's a minus 3/4. This is going to be plus root 3 over 2. 4 squared over 4, that is going to be 4. 1/2 of 4 is a minus 2, and then a minus natural log of 5. Then this is going to be our 3/4 again, a minus 3/4. This is going to be a plus root 3 over 2. And then this is the same term as that. So after all is said and done, we have 2 natural log of root 3 plus 1. We have 2 of these root 3 over 2 terms. And so we would say plus root 3. We have a minus natural log of 5. And then we have 4 minus 2, which would be 2. And then 2 minus 3/4 minus 3/4. That's 2 minus 1/2. So we get plus 1/2. In theory, that's the exact answer. It's a theory because, again, these are just so computationally tedious that if you make a sign mistake somewhere, or if you square something incorrectly, or do any of those little bitty mistakes, it's very easy to make some tiny mistake that'll throw the whole thing off. Let me plug this into a calculator so we can get the approximation. 2 natural log of square root of 3 plus 1. And then it is plus the square root of 3 minus the natural log of 5, and then plus 1/2. Oh, and I have a syntax error. Of course I do, because there should not be a parenthesis at the end. There we go. So I end up getting 2.633. There we go. Not too bad. Now, what I'd be curious about is I'd be curious if Desmos could actually do that. Let's take a quick look. So if I asked it to do the integral, no, it's not going to do it. That's okay. Wolfram Alpha might be able to. And so if we go to Wolfram Alpha, it may or may not be able to find the area between these two functions. And so let's see if we can say area between 1 over x plus 1, and I need some parentheses there, and x minus 1 over 2 on 0, 4. It might be able to handle it, it might not. We'll see. Wolfram Alpha, again, is the calculator that mathematicians use. So the area between these two on 0 to 4, and notice that it actually gives the exact same thing that we have. The 1/2 plus the square root of 3 minus the log. And remember that when Wolfram Alpha writes log, it means the natural log of 5 plus 2 times the natural log of 1 plus square root of 3. It dropped the absolute value since it was already positive. And when you calculate that out, you get the 2.6327 or 63272, which is what we got. Cool. It's always nice when you do a long series of computations and the calculator gives you the same answer. And so that's the first application that we have, finding the area between two curves. Hopefully that wasn't too bad. It's very, very tedious, and hopefully that is the lesson we took from it. The next application is a lot less tedious, and there's not a whole lot to think about there. And so the next one is the average value of a function. And so you remember how to find the average or mean back in arithmetic. You add up all the elements and then you divide by how many elements you have. Well, to find the average value of a function, it's basically the same. The only difference is we divide by the interval. And let's see if we can see the visual for what's going on here. And so let's stop the share again, and we'll try and understand the visual. So let's create some function, and we'll say that this is our function right here. Now, the question is, what is the average value of this thing on the interval from A to B? And it might not be very clear where it is. We kind of guesstimate that it's going to be somewhere in like here. And when we're talking about average value, we're talking about the average Y value. And so the average Y value might be around there, probably a little higher though. It's probably higher, probably closer to like right here maybe. I'm thinking this section here would probably fit almost in over here. And so this might be it. The way we can figure it out though is if we had some value, which was the average value, and let's just say that this is the average value, then the area of this rectangle here should be the same as the area underneath the blue. And we can find the area underneath the blue because we know the area underneath the blue is going to be given by our integral. And so the area is equal to the integral from a to b of, let's call this function f of x dx. Well, we also know the area of this rectangle. If this height is equal to, let's say, y naught, then the area is going to be just the base times the height. And so that height is y naught, and then it's going to be times a or b minus a, because b minus a is that length there. Well, this y naught value is what we're calling the average value. And so in order to solve for that average value, all we have to do is divide both sides by b minus a. So the average value is going to be equal to 1 over b minus a times the integral of f of x from a to b dx. And that's our formula. It's not too bad. And once you have the formula, well, you just apply the formula whenever you need to apply the formula, and you're good to go. So I have 3 examples here. I mean, none of them are that tricky. It's just integrating. And so let's try that first one, just so that we can see one of them. And so it says, find the average value of x squared on the interval from 0 to 4. So average value of y equals x squared on 0 to 4. And so all we have to do is use our formula, and we're done. And so the average value is equal to 1 over b minus a, which is the length of the interval. In this case, it's 4 minus 0. The integral from a to b of the function. Well, that's 1/4. The integral of x squared is 1/3 x cubed. And then we evaluate from 0 to 4, which gives 1/4 of 1/3 of 4 to the 4th minus 1/3 of 0 to the, or sorry, 4 to the 3rd. My bad there. And then 0 to the 3rd. This term goes away. 4 cubed is 64. 1/4 of 64 is 16. And so we get 16/3. So if we want to think about what that physically represents again, we can go to our good friend Desmos. And so 16/3 is what we ended up with. And if we pull up Desmos, and let's just get rid of all of these. There we go. And so our function is f of x equals x squared. And we were just talking about it on the interval from 0 to 4. Or 0 less than or equal to x less than or equal to 4. And so this is what it looks like. If we wanted to figure out what the area underneath it looked like, we could say 0 is less than or equal to y is less than or equal to f of x. And that gives us the graph of the area from 0 up to that value. To figure out what the average value is, well, we just found the average value to be 16/3. And so let's say g of x equals 16/3. And we will also restrict that on the interval from 0 to 4. In theory, the area underneath g of x is going to be the same as the area in purple. And so let's see if I can write that 0 less than or equal to y less than or equal to g of x. So the area in purple and the area in red are the exact same area, which tells us that this height is the average value. Average value is basically saying if it's all water and it were to level out, what would that level be? And that level is 16/3. And that's the average value. It's a very, very easy thing to calculate. We also have the mean value theorem for integrals, which, there's nothing that interesting or valuable for our course related to it, but here it is. If f is continuous on a to b, then there exists some number c in AB such that f of c is equal to the average value of f on AB. What that is saying is if we think of our graph, notice that there's a point here where our average value is crossing our starting function. As long as our starting function was continuous, it's guaranteed that these two things are going to cross, which means that there is a point, in this case, 2.309, 5.333, where the function actually attains its, its average value. If the function's not continuous, we're not guaranteed that. But provided the function is continuous, we're guaranteed that we will hit that value. Again, finding biological and medical applications for that might be a little tricky, but I guess you could. What this comes from, of course, is the intermediate value theorem, because we know how the intermediate value theorem works. We are basically guaranteed that we're going to attain all values between our low point and our high point, and our middle better be between our low point and our high point. And so that's the quick and dirty proof of that. And so that's average value. Notice average value went much, much quicker because the computations for these are much quicker. You're almost never going to end up with 12 terms that you have to evaluate and simplify. And that makes them go very quickly. The next one actually has a lot of applications for folks, but you might not see the applications as much because most of the work will already be done for you if you're going into medicine at least. So suppose that we have some arbitrary three-dimensional object. Does not matter what this looked like. Oftentimes we think of them as kidney shapes, which is kind of works for biology and medicine because we'll actually be using kidneys as one of the examples. And so if we wish to find the object's volume, one way we can do this is take a series of cross sections and estimate it using prisms. And so in this case, sometimes cylinders work, but they don't necessarily have to be cylinders because if it's not circular, then it's not going to be a prism. But if A of x is the area of the cross section and its width is given by delta x, then we are adding up all terms of the form A of x times delta x. And if we take the limit as we use infinite cross sections, we get our standard integral. And so this is the formula for the volume of something when we know what the cross-sectional formula is. And so if we know what all of the cross sections, what the area of all of these cross sections are, then the volume is just going to be the integral from A to B of A of x dx. Now, of course, you're typically not going to have a nice formula for the area or cross-sectional area of a kidney or a liver or something like that. But what you will have is you will have CT scans. And CT scans will tell you what the cross-sectional area is at a series of points. And you can use that to calculate the volume fairly quickly. And I believe that the computers are already designed to do that for you. So you might not have to do too much on that. What we will do, though, is we will practice a couple of these. And the one we'll practice in particular is the solid of revolution. And so a solid of revolution is basically saying that instead of dealing with some random shape, we're going to make this a shape which is rotated around the x-axis. If you did math 402 or 401, you'd actually be dealing with a number of different cases. We're going to keep it easy. We're just going to be rotating it about the x-axis. And so suppose that we have some function which you want to know the volume of the object created by rotating it about the x-axis. Then the cross-sectional area is a of x equals pi times f of x squared. And the volume is integral from a to b of pi times f of x squared dx. And I have a number of practice problems here, but honestly, most of these practice problems are designed to be a little bit trickier and give you some interesting results. If you want, play with these. For now, though, I think I'd prefer to just make sure that we understand how to calculate these in general, the types of problems that you might see on your homework. And so let's take a function and we'll just pull up Desmos and find some nice function which is positive on a region. How about, I would like to do f of x equals sine of 4x. 4x might be too much. Let's do 4x, and then let's do plus 1/2 x. Ooh, I meant for that to be 1/2 x. Plus 2. I guess I do want this to be something different. Let's make this pi over 2. And then let's figure out the area or the volume of an object from 0 to 10, which is rotated. And so we will restrict this on the interval from 0 to 10. And so this is the shape which we are going to be dealing with. And so I will write down the problem so that we can practice it. It will be find the volume of the object formed by rotating the function f of x equals sine of pi over 2 x plus 1/2 x plus 2 about the x-axis on the interval 0, 10. Cool. And so I will stop the share so that we can see that all written out. So find the volume of the object formed by rotating the function f of x equals sine of pi over 2x plus 1/2 x plus 2 about the x-axis on the interval 0 to 10. And let's sketch out what this is actually doing so that we can really understand that. And so let me quickly draw what the graph of this looks like. And so on the interval from 0 to 10, looks like it's going to go almost as high as 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. It starts around 2. Let's even see, where does this end? Oh, it ends at 7. All right, good. And so this is going to be starting at 2 and going out to 7 by the time we get out here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. That's where we're going to be ending at. And so our graph is going to be starting here, and it's going to be ending at 7, which is right around here. And we could potentially figure out all of the midpoints if we wanted to. It'll be something like this. And it'll be going up and then down and then up, and then down, and then up. So this is what our starting curve is looking like. What we're going to do is we're going to be rotating this all of the way down. And so we would basically be recreating this down here on the bottom. And so that would be coming down around here. And we could even put some midpoints in here if we wanted to. And again, I'm just going for a sketch so that we can kind of visualize things. My sketch is definitely not perfect, but that is okay. But this sketch, it would start by going up and then down, just like all of these others. And so now it's going to go down and hit this and go up and then down and then up and then down and then up. And so in theory, this down here is the reflection of this function up here. And so while this is f of x, this looks like negative f of x. What we're going to be doing is we're going to be kind of visualizing this in 3 dimensions and wondering what would happen if we were to take this and create a 3-dimensional object of this. And so at every single point, this is going to be coming down and going back up. It's going to be coming down and going back up. And we're going to get this 3-dimensional vase out of this. What we're being asked to do is find the volume of this vase. And that's what this volume of revolution is all about. Now, the computations aren't too terrible because really all we have to do is figure out what the cross-sectional area is and then integrate that. But we can find the cross-sectional area because we know that the area, so let's say cross-sectional area, is always going to be given by pi times r squared. But our radius in this case is just going to be the height of the function. So that's where it's pi times f of x squared. Oh, and now I see why I did not want to do this. Oof, I have given myself something which is going to be almost impossible to do, and I feel terrible about it. Should have gone with one of the examples that was standard or already in the notes. And I'll show you why. We've basically given ourselves something which we might not have the tools to actually evaluate. And so in order to figure out what the area is for this one, or sorry, what the volume is, the volume for this is going to be given by the integral from 0 to 10 of this function squared times pi. And that's where I made the mistake in this problem and why I should have gone with one of the pre-written ones. So sine of pi over 2x plus 1/2 x plus 2 squared. And this is a very, very difficult thing to integrate. We do actually have the ability to integrate this though. And so maybe I'll walk you through that so that you can see how you would go about a problem like this. But we do have the ability to integrate this thing. It's just not very pleasant. So in order to integrate this thing, the pi we could factor out, and we could just keep the pi there the entire way through. But we're going to need to FOIL all of this. And in foiling this, we're going to get something that is not very pretty. The integral from 0 to 10 is going to be a sine squared of pi over 2x plus it's going to be the 1/2 x squared, which is going to be 1/4 of x squared plus 4. And then we have all of the cross terms. So this times this and this times this is going to give a x times sine of pi over 2x. Then it's going to be the 2 times it. So plus 2 times the sine of pi over 2x. And we'll have 2 of those, so it'll actually be 4 sine of pi over 2x. And then it's going to be plus this times 2. So that's going to end up being 2x. dx. Each of these we can integrate. They are not going to be very nice though. And so this one, we can integrate using integration by parts. Alternatively, we could integrate this using a trig identity if we wanted to, because sine squared is something we can play with a little bit. This one we can integrate, no problem. This one we can integrate, no problem. The x sine of pi over 2x, this one we can also integrate by parts. This one we can integrate, no problem. This one we can integrate, no problem. But after we've gone through that whole process of integrating these two things, which are much more challenging to integrate, we're still going to have 6 terms, and then we're going to have to evaluate them at the 0 and at the 10. And when you do that, you get something which is very not nice. And so this is a fun one. If you want to challenge yourself, give this one a shot. But for the purposes of this video, this might be a little bit too much. And so let's transition back to an easier example. And I will go with one which is in the notes, since that might be a little bit nicer. And so the one which I will go to from the notes, this is evidence that I should never deviate from the notes, will be this function, the square root of 1 plus 3x squared. And it'll be on the interval from -3 to +3. The process for this one is going to be almost exactly the same. But the integral at the end is going to be much, much nicer. And so let's go through this process. And so again, the visual is going to be very, very similar. But now the function we're dealing with is the square root of 1 plus 3x squared, which looks almost linear, but not quite. Graph of this on the interval from 0 to 3 would look kind of like this, I believe. Let me quickly double check that that's what it would look like before I say that that's what it looks like. Using Desmos real quick. 1 plus 3x squared. Yeah, that's roughly what it looks like. It's actually a little bit steeper than that, but that's okay. So it looks something like this on the interval from 0 to from -3 to 3. So what we're going to be doing is we're going to be taking this shape on the interval from -3 to 3, and we're going to be reflecting it. And we're going to be visualizing what it would look like if we took this and we rotated it around. And this is what the shape looks like. And so now we have a new vase. The cross-sectional area is still going to be given by pi times the function squared. And so pi times the function squared, where this is our function. The reason why this one is much, much nicer now is because we're going to be doing the integral from -3 to +3 of pi times the square root of 1 plus 3x squared squared. And that is a much, much nicer thing to integrate, and is probably more in line with what you'll see in the homework. And so if we wanted to do this, we could factor the pi out. We don't have to if we don't want to, but it might make it a little nicer looking. But this will be pi, the integral -3 to +3, and then it will be just 1 plus 3x squared. Because the square root and the squared cancel each other out. Technically, it gives you an absolute value, but we don't have to worry about that. Actually, it would if it had been the other way around. Regardless, it doesn't matter for this situation. Now we're just integrating. Pi can hang out. Integral of 1 is x. Integral of 3x squared is going to be x cubed. And now we just have to evaluate. So we're going to get pi. We could keep the pi there, I guess. Evaluating at 3, we get 3 plus 27 minus pi times -3 plus -27. Canceling out all of our signs. 3 and 27 is 30, and 30 gives us a total of 60 pi. And so the volume of this object is 60 pi. And that's how these problems will typically go. I mean, there's nothing terribly difficult about them except for the integral itself. In this case, the integral was very nice. On that first example problem I gave, the integral was very not nice. Depending on the type of problem you have, you could end up with something nice, or you could end up with something which is a disaster. The ones in the homework should all be fairly nice, though. Now, there is another type of problem which you will see in the homework, and that is using the idea of CAT scans, because CAT scans are a very simple application of this stuff. What a CAT scan does is it takes the cross sections, and you can then measure the area of those cross sections. And so a CAT scan produces equally spaced across sections, sectional views of human organ that provide information about the organ otherwise obtained only by surgery. For example, such measurements of a liver volume can be related to diseases such as cirrhosis. Yeah, we know that. Suppose that a CAT scan of a human liver shows cross sections spaced 2 centimeters apart. The liver is 20 centimeters long, and the cross sectional areas in square centimeters are 0, 39, 63, 128, 117, 106, 94, 79, 54, 18, and 0. What would you approximate the volume of the liver to be? Well, here's a fun thing about this. This is actually just the Riemann sum stuff that we were doing in a previous section. And so as long as you remember how to do Riemann sums, you're good to go. It's just instead of talking about areas, we're talking about volumes. And so you could do the left endpoint Riemann sums or the right endpoint Riemann sums. Our delta x is going to be 2. And whether you do left or right, the zeros just going to cancel out anyways. And so that one will not matter. And so in order to calculate this, you would just take 2. And so the volume 2, and then it would be multiplied by the sum of all of those values, except for one of the endpoints. So 0 plus 39 plus 63 plus 128 plus 117 plus 106 plus 94 plus 79 plus 54 plus 18. And that will give you the volume, or an approximation for the volume. And I will throw that into my handy dandy calculator. 39, 63, 128, 117, 106, 94, 79, 54, and 18. And then multiply by 2. I end up getting 1396 cubic centimeters. (1396 centimeters cubed). And so this is a little bit more than a liter. That's 1 1/3 liters, basically. And that seems like a reasonable size for a liver, though I'm certainly not the liver expert. And so that's the other type of volume problem which you'll be seeing. It's one where you're given the cross-sectional values and you're just asked to create an approximation. Now note, with this one, we used the left endpoints. If we had used the right endpoints, this 0 would have been going at the end. We could potentially have used midpoints, but if we'd used midpoints, we would have only used 5 values, which means it probably wouldn't be as accurate as using the left or right endpoints. You might have been able to use the trapezoid rule, but the trapezoid rule would actually give you the same because the left and right values would have been the same anyways. And so, yeah, as long as you have 0 at both ends, the left and right and the trapezoid rule are going to all be the same anyways. And so you might as well just use all those values. The last application problem we have is one which is using an advanced population model. And there are a ton of advanced population models. This is just one of them. And it's a pretty good one. This is one which deals with the idea of new elements being added into a system while elements are also being removed from a system. So if we know how elements are increasing and decreasing with time, we can actually create a fairly nice model. And so suppose that we start with an initial population of P0, and new members are added at a rate of R of t, where t is the number of years from now. Additionally, suppose that the proportion of the population that is expected to survive t years is given by S of t. And so we have R of t is the number of new members added, and S of t is the survival rate. To predict the population in big T years, we can use the following population model. And so this is P of big T is equal to S of big T times P0 plus the integral from 0 to big T of S of big T minus little t times R of little t dt. This messes a lot of folks up, the idea of having these two t's in here. This little t here is often called the dummy variable because this little t goes away when you actually do this computation. And it didn't matter what this little t represented. It represents basically how time changes along the interval from 0 to t. And this integral here is saying how the population itself is changing based from what you would expect if you just had the initial population surviving. If you want, you can try and go into how you come up with this, but that might be a little bit more advanced than what we want. What we really want is we want you to be able to calculate things using this model. And so let's do number 1. Number 2 is essentially the same, but let's do number 1. And I'll write all of the information out as it comes along. So we'll start with this formula. P of t is equal to S of big T times P0 plus the integral from 0 to big T of S of big T minus little t times R of little t dt. And so for number 1, it says, suppose that there are currently 5,600 trout in a lake. And so that 5,600 is our initial population. And so P0 is equal to 5,600. And the trout are reproducing at the rate R of t equals 720 e to the 0.1 t. And so R of t is equal to 720 e to the 0.1 t. Pollution is killing many of the trout. The proportion that survive after t years is given by s of little t is equal to e to the negative 0.2 t. How many trout will there be in the lake in 10 years? And so that represents our big T. All right. And so now we have our formula that we're using. We have our given information. I put this line straight through that zero. That was unintentional. There we go. And so let's just figure out the pieces that we still need to figure out. So looking at this, we have s of little t. This is saying s of big T. And so s of big T would be equal to e to the negative 0.2 big T, which is 10. And we could even multiply that out and give us e to the negative 2. We then have P naught, which we already have. We have S of big T minus little t. That's going to be the complicated one. So S of big T minus little t. Well, big T we know is 10. And so this is S of 10 minus little t. And so looking at our S of t function, that's going to give us e to the negative 0.2 times 10 minus little t. Now, if we remember our algebra 2, we can clean this up. So cleaning that up, we are going to get e to the negative 2 times e to the positive 0.2 t. And then we have r of t, which we already have. And so at this point, we have everything we need to rewrite this expression. And so p of 10, let's go green pen for now, as all of my pens go flying. There we go. And so p of 10, which is what we're trying to find, is going to be equal to s of big T, which we already know is e to the negative 2, times P naught, which we know is 5,600, plus the integral from 0 to 10 of s of big T minus little t, which is this right here, e to the negative 2 times e to the 0.2 t times r of t. And r of t is 720 e to the 0.1 t. Looking at this, we can see that we have two parts. The first part is this bit right here. We'll just call that number 1. And then this part right here is the more complicated part 2. Part 1 is done. We can plug that into a calculator and be done with it. Part 2 is not done. And so let's see if we can just take part 2 and clean it up a little bit. And so it's going to be the integral from 0 to 10, but we have a 720 and an e to the negative 2, which we could just pull out because they are just numbers. The e to the 0.2 t and e to the 0.1 t, we could combine, giving us an e to the 0.3 t. And that's something we can integrate. The 720 e to the negative 2 just hangs out. E to the 0.3 t, when we integrate that, we'll get 1 over 0.3 e to the 0.3 t. which we're then evaluating from 0 to 10. The 720 e to the negative 2 can hang out again. Evaluating this at 10, well, we could clean this up and make it a 10 thirds. And we could even factor that out if we wanted to. And then it'll be e to the 0.3 times 10 minus 10 thirds e to the 0.3 times 0. And now that we can clean up. And so let's see if we can bring everything back together. And so we will get P of 10, the fish population in 10 years, is equal to e to the negative 2 times 5,600 plus 720 e to the negative 2 times 10 thirds. And that's factoring the 10 thirds out. Then it's going to be e to the 3 minus e to the 0, which is just 1. At that point, we can plug it into our calculator. So e to the negative 2 times 5,600 plus 720 times e to the negative 2 times 10 thirds times e cubed minus 1. And I end up getting 6,957 when we round. So this is saying that in 10 years, we would expect the population to be 6,957 according to this model. And so that's how you would do a problem like this. Now, something you might note is how do we actually come up with these equations? And that is something which is fairly tricky when you're talking about fish populations. You can come up with some approximations, but like it said, it was tied to pollution, and that'll make it so that that function will change possibly over the course of years. And that makes it difficult. The second example, which we won't do, is very, very similar, but now it's actually stuff you can calculate a bit. And so this one is saying a drug is administered intravenously to a patient at a rate of 12 milligrams per hour. And so that 12 milligrams per hour is the rate at which it's being added, your R of T. The patient's body eliminates the drug over time so that after T hours, the proportion that remains is e to the negative 0.25 T. That's something that can be measured, and because those things do decrease in the bloodstream exponentially, you could actually come up with this model if you had the resources. If the, and this value here is the S of T rate. And so that would be S of T. If the patient currently has 50 milligrams, so that's your P naught of the drug in her bloodstream, how much of the drug is present 8 hours from now? And so that would be 8 is our big T, because everything is measured in hours. And so you could go through the exact same process and you could calculate it without too much trouble. But this is how you would calculate the amount of drug currently in a person's system. And if you know that a drug is only effective if it's within a certain threshold, then administering it intravenously might be the way to make it so that it is constantly at a fixed level. And again, a lot of that work's already going to be done for you as you go into the field, but now you can understand how it works. Why is the prescribed amount given as such? And that brings us to the end of today's lesson. Today's lesson had its ups and downs. We started with the idea of area between two curves, which is not a difficult concept to understand, but it can become computationally very tedious. We then did average value, which is a blink and you miss it moment because it's just this formula. And once you have this formula, you're done. We then did the volume of a general solid, and I made the mistake of trying to come up with my own problem instead of just using the ones that I'd already come up with. And it ended up a little bit rougher than I had intended. If you want, you can still go back and work through that problem, though. The sine squared one might be the hardest one to integrate, but the rest of them should go fairly painlessly. And then we also talked about the idea of how we can use these to model things like CAT scans. And so if we have cross-sectional area, we can approximate these things. We then did an advanced population model, and there are tons of advanced population models out there. And as you do your research for your project, I'm sure you'll see some of those pop up. And so it's definitely worth trying to understand how models like this come into be. For now, I just want to make sure that you know how to actually calculate them. And that brings us to the end of today. We just finished chapter 6. Next, we're going into chapter 7, which is all about differential equations. And I'll be teaching you a few advanced techniques when it comes to chapter 7. Chapter 7 and chapter 10 actually go together very well. But in order to fully understand some of the techniques, you do need to have some other things, in particular, some linear algebra, some advanced calculus, and a little bit more differential equations. That's what chapter 7, 8, and 9 are all about. But chapter 7 is really getting you prepared for chapter 10 and for understanding how chaos theory works and how you can use it to understand different advanced models. For now, though, you have plenty of work to do, and so I will let you get to it.